Hey, welcome back to AI Tech Hub. I'm Techie. Today's explainer is diving into something absolutely foundational in the world of artificial intelligence. We're looking at the geometry of meaning, and specifically, we're going to decode AI embeddings. So, if you've ever played around with modern AI and wondered, how the gears actually turn under the hood, like how it seems to genuinely understand what you're typing to it, well, this is exactly where you need to be. We are looking at the ultimate translator between human abstraction and machine logic. Because think about it. Human language is super messy. It's emotional, it's packed with context and nuance, but machines, they're cold, they're calculating. They are built on pure structure. So there has to be a bridge, right? A way to translate our flowing, abstract thoughts into a format that a machine can actually chew on. That bridge is what we call an embedding. And getting this concept is literally the key to understanding how modern AI works.
So let's start with a really basic question. How does a computer actually turn words into meaning? To get this, we kind of need to step back and realize why computers require a totally different approach to language than we do. At their core, the CPUs and GPUs running these massive AI models are, well, they're basically just giant, super complex calculators. They don't process concepts, they definitely don't feel emotions, and they don't inherently understand letters or words at all. They process electrical signals that represent binary math, just ones and zeros. So to a computer, a word like apple in its raw text form is completely useless. It's just a meaningless string of characters. A machine can't compute apple. It can't add, subtract, or compare apple to orange in any logical way unless those concepts are represented mathematically. The computer absolutely demands numbers. If we want a machine to process the concept or the feeling or the context of a word, we have to find a way to take that raw meaning and turn it into a mathematical value.
Now, to really wrap our heads around how we do that, let's think about a system we literally use every single day: GPS coordinates. This is our baseline analogy for today, and it is incredibly powerful when you break it down. Think about any physical location on Earth, right? It could be your favorite neighborhood coffee shop, the snow-capped peak of Mount Everest, or just a totally random spot in the middle of the Pacific Ocean. Every single one of these wildly different, super complex places can be pinpointed perfectly using just two numbers: latitude and longitude. You don't need a photograph of the place, you don't need a written description of the weather, and you don't even need to know the street name. Just those two floating point numbers give you an exact mathematical point on the globe. It is essentially the ultimate compression of physical reality. The entire complexity of a dense city is just stripped down to a simple mathematical address.
But the real magic of these coordinates is how they relate to one another. Think about the mathematical relationship between those numbers and actual physical distance in the real world. Places that are physically close together, like say two houses on the exact same street, they're going to have very similar GPS coordinates. The numbers are almost identical. On the flip side, places that are physically far apart, like New York and Tokyo, well, they have wildly different coordinates. This means that numerical similarity directly represents physical proximity. And because of this, we can actually do math with physical locations. By just subtracting one set of coordinates from another, a computer can instantly calculate the distance between two cities, or figure out the most efficient route to travel, or even estimate how much gas you'll need without ever actually looking at a physical map. The math just tells the whole story.
Okay, so an embedding is this exact same concept, but instead of mapping physical locations, it maps meaning. An embedding takes a word, a sentence, or even an image and converts it into a list of numbers that act as exact coordinates. But rather than plotting a point on a map of the Earth, they're plotting a point in what we call a meaning space. It's basically a massive mathematical map of human concepts. Now here's where it gets incredibly fascinating. A physical map really only needs two dimensions, right? Latitude and longitude, because the surface of the Earth is two-dimensional. But human language is vastly more complex than a flat map. You cannot capture the nuance of language with just two numbers. So to map meaning accurately, AI models use hundreds or sometimes even thousands of dimensions. Imagine a highly complex, invisible GPS system that tracks not just north and south or east and west, but plots coordinates along thousands of different conceptual axes. We're talking emotion versus logic, past versus present, royal versus commoner, abstract versus concrete. A single word gets a coordinate on every single one of those hundreds of axes, giving us a massive, high-dimensional list of numbers that perfectly pinpoints its exact location in the universe of meaning.
So you might be wondering, how do these coordinates actually get assigned in the first place, and how does the AI use them? Well, these high-dimensional numbers aren't just assigned randomly by programmers sitting in a room somewhere. They are generated by massive neural networks that have been trained on billions of words, literally reading the entire internet. By constantly looking at which words appear near each other in sentences over and over again, the AI learns context and assigns these coordinates automatically. And just like our GPS analogy, in this high-dimensional meaning space, concepts with similar meaning end up mathematically close together. The machine uses a distance metric, often something called cosine distance, to measure the gap between these points. Let's look at a concrete real-world example, like search engines. If you go online and search for the phrase affordable kicks, the embedding, the coordinates for that phrase, is mathematically incredibly close to the coordinates for cheap sneakers. Because the cosine distance between those 2 points in the meaning space is so tiny, the search engine knows exactly what products to show you, even though the actual letters and words you typed are completely different. Semantic distance literally becomes mathematical distance.
Now, for those of you who have been following our deep dives into AI architecture, this is the massive aha moment where everything clicks together. These embeddings, these high-dimensional lists of numbers, they are the exact same thing we were talking about in our vector database explainer. When we discuss taking data and storing it so an AI can rapidly retrieve it, this is the mechanism. An embedding is what turns human text into that specific list of numbers we kept referring to as a vector. They are literally one and the same. Furthermore, this is the invisible engine powering RAG, or Retrieval-Augmented Generation, which we explored a while back. When a language model needs to retrieve external documents from a massive company database to accurately answer your question, it relies entirely on the mathematical proximity of these vectors. It translates your question into an embedding, measures the cosine distance to all the document embeddings in the database, and then retrieves the ones mathematically closest to your prompt. It's all connected.
By turning human language into pure high-dimensional math, embeddings have essentially given machines a highly precise map to navigate the complexities of the human mind. It is a stunning feat of modern computer science that allows these rigid, calculating machines to interact so fluidly with the beautiful messiness of our words. But as we wrap up this explainer, it leaves us with a truly provocative question to ponder. If an artificial intelligence can perfectly calculate the exact mathematical distance between a concept like love and a concept like heartbreak, does the machine actually understand what those words mean? Or is it simply the world's most advanced, high-dimensional GPS for vocabulary? Definitely something to think about the next time you're interacting with these amazing tools. Now, do you want to see an embedding actually created from real text? Let me know. Drop a comment down below and just type embed. Make sure to follow for more and definitely leave your suggestions for what topics we should tackle next. See you next time on AI Tech Hub.